Again, here it's a very brief video. The reason for that is by now, because of the style with which we covered different modalities, it will be pretty, you could guess what is the image quality that we are going to talk about, what are the metrics, right, of image quality, and more importantly, our interest is to see how do we relate the image quality to parameters that we studied, that is the physics and the instrumentation or the data acquisition, right? So first we will focus on sampling parameters, and the reason for this is that is related to resolution. So first we want to talk about resolution and then signal to noise ratio. Of course, we already spoke about contrast, right? Contrast mechanism before. So once we have noise, you know, contrast to noise ratio you can arrive at. But so the emphasis here will be essentially to bring the noise part of it and the resolution part of it, which is resolution very key. And the challenge with the resolution, so we'll spend actually considerable time even within this short module on the resolution part. And the reason for that is everything is in front of the eyes. You think you understand, but to interpret that is little confusing, right? So anytime something is confusing, that means you should really understand it to the core. That way you don't have to memorize anything. If you close your eyes and think about the concept, the definitions and the metrics should come out as a visualization for you. I mean, that is the aim that I have. Okay, and so resolution is tricky. You might feel like it's straightforward, but it can get you confused, really, right? So we'll start with resolution first. I mean, before we formally get into resolution, we'll have to talk about sampling, because the data that you're collecting is sampling. Remember, first we started with Z selection. So you already have a slice thickness delta Z. That delta Z is controlled by your RF excitation frequency bandwidth. In fact, some level we covered ideal slice thickness and your actual slice thickness, because you have a finite sync pulse, right? And therefore we already talked about blurring within the edge of the thickness slice. Okay, so somewhere you already realize sampling becomes an important issue. But we will now focus on not the thickness as much. For a given thickness, because we are interested in image, even though we know even in the thickness direction there is blurring happening because of your delta Z, right? How you sampled the frequency of your RF excitation is not hard limited, but it has a ramp up and a ramp down. So we leave that. We are more interested in plane, right? Within the image quality or image resolution, or rather image sampling first. Okay. So within each slice, we are actually talking about sample and frequency. I mean, this is again the bigger problem in this domain. Each time we think about sampling, we introduce the concept X of t or Y of t in time domain, the signal in time domain, and we say, oh, sample it at twice the highest frequency to beat the Nyquist, right? And that's how we do the sampling concept. Here it is kind of weird. The signal that you are recording, as we saw, is actually the frequency spectra. So what you are recording is a sampled version of your frequency spectra. Okay, so that's where the confusion may start to arise. So in each slice, we are going to talk about the data that we acquired is a sampled case space or sampled Fourier domain is what you have. Okay, in case of rectilinear, we will be talking about delta U, right? Delta U is in the X direction. You remember that the ADC that we were plotting in the pulse sequence diagram. We just said TS, ADC is on for data acquisition time, TU. But essentially that's a sample. ADC is analog to digital, right? So essentially you have sampled acquisition of your frequency domain. Delta V, in some sense you already saw, it was a line that we put, a horizontal lines that we put, right? So there was a spacing. So that is actually discretized in some sense. U was, we put an arrow mark as a line. So we always thought that it is continuous, but actually speaking, it's sampled data points is what you have there. Delta V is more intuitive, okay? But we will have to relate these two. In case of polar scan, likewise, you have angle that is discretized. You saw the theta steps, so that you it's already vivid that you have discretized. But there also along the row, we put a straight line, we didn't put points. Essentially it is points, but we have been using line, right? So the sampling that you have there is also there. So delta rho should be there. So for the purposes of covering the topic and giving this intuition, we will stick with the rectilinear scans only in the discussion going forward. Okay, because it's easier to visualize rectilinear than angles. Okay, so let's start with sampling, right, in U direction. What happens in U direction? So here is our rectilinear scan. Only things that I have added is, remember this was TS before one box. Now we are actually saying this is ADC, so we are actually sampling. So we are recording the signal, whatever signal that is coming. In this case, it is a spin echo, right? The echo from spin. So spin echo signal. The signal is recorded over this time, but with some time period capital T. Okay. Likewise, in the other, so this is your capital T. Likewise, when you are repeating the experiment, you are moving the phase direction, your gradient, the delta Gy, and you are applying the phase sequence or phase encoder for TPE. So your delta U is gamma Gx T. Remember, we were talking about the highest frequency as gamma Gx Ts. Now that means gamma Gx times this T is going to be your frequency delta U. Likewise, your delta V will be gamma delta Gy operated for TPE. So same jargons that we did before, but now since the T is not, before we had TS, now this T is one time period, therefore your delta U is your delta U. So we have been putting this arrow line, but essentially more correctly what we should have put is, we should have put sequence of dots, right? And the distance between the two dots or the two samples would have been delta U here. This direction it is intuitive. We always put discrete step. Okay, so this is what we have. Now what we need to do is understand the relationship between delta U, delta V, no, the total U, total V. More importantly, this is just Fourier domain. We are interested in the image resolution, right? In the imaging plane. So what happens when you start with this? What is its effect on the delta X, delta Y, right? That is what we want to see. The X and Y are spatial domain, whereas U and V are frequency domain. So recall, each pulse sequence contains ADC window. Data are acquired by ADC. So if you have n samples over TS, then one capital T, that red capital T that we showed in the previous slide, is nothing but total time period TS of acquisition divided by total number of samples that are acquired. So your sampling interval or sampling rate, sampling frequency, right, is 1 by capital T or n by TS. So sampling step in U, so always we work with, so that gets you your delta U. Sampling step in U means delta U. In the U direction, how you step delta U, that's what. So in the signal is demodulated and then sampled. So that means that before you do that, if you do ADC, always we are interested in anti-aliasing. So you need to do anti-aliasing filter. Anti-aliasing filter you have to do for highest frequency, correct? That is the whole idea. I want to do Nyquist. Similar concept here. It's the same signal. So anti-aliasing now you do with support of Fs by 2 plus Fs by 2, meaning your bandwidth is Fs, right? You have to be sampling better than that so that you don't lose any information. So your ADC should have anti-aliasing filter with a frequency bandwidth that is corresponding to your received bandwidth. This Fs can be obtained from here, right? Fs is 1 by T, so all this is coming from there. So your readout X gradient relates to your, so this is frequency domain. What we want to understand is what happens to your spatial domain because of the sampling in frequency domain. The data is acquired as samples in frequency domain. What is its effect on the delta X in the spatial domain, right? So you can relate the frequency to space because of this gradient. X gradient relates to normal frequency by V naught plus gamma Gx X. Correct? So that means you can already recognize only signals which are within this bandwidth, right? Receiver bandwidth. Or in some sense you have a gradient in field strength dictates the frequency range. The frequency range and the sampling of it should dictate your X direction. So your X only signals with frequency within this are measured. So your X minimum will correspond to X naught minus Fs by 2 by gamma Gx, X maximum, right? So this is spatial. Minimum X to maximum X is related to this gamma Gx and Fs. And therefore your field of view of your image width and image height, right? So your image width, if you will, if you call that as the X direction, your image width is what? X max minus X min. Your field, or we can call it as field of view in X direction, is X max minus X min, which is, if you substitute this, Fs by gamma X, this is nothing by 1 by gamma X. Oh, this we know. What is this? Remember, gamma Gx T, capital T is time period of in your ADC. So that means this is nothing but our delta U. Delta U is gamma Gx T. This is, oh, so your sampling of frequency domain dictates your field of view. So the finer I sample, the larger the field of view I can get. The sparser I sample, smaller will be the field of view that I get in X direction. So similarly you can think about in V direction, right? Phase encoding gradient Gy, your phase is gamma Gy TPE, this is the step size of your V direction. So each time you change Gy by delta Gy, you are changing, right? Your A is becoming Gy TPE by delta A. So recall the previous slide and the plot, right? How we jump. So this is just extension from there. So your step size is delta V in the V direction, that is dictated by your gamma delta AY. Clear? That means your field of view in Y direction. So this is step size in V direction, frequency domain in V direction. Your field of view in spatial domain is 1 by gamma. So this is also inversely related. So the idea is, if you step finer here, that is in your phase encoding, you have finite phase or fine phase separation, then your field of view in Y direction will be increased. Clear? However, here notice there is no explicit anti-aliasing filter. So therefore you can get anti-aliasing, means you are going to get aliasing means, remember the crude definition that you will remember from textbook. High frequency masking or masquerading the low frequency. Here in spatial domain, what are we talking about? Here what is going to happen is the manifestation would be the wraparound. So if you are taking a head scan, right, the front part can go in the back. It will wrap around. If you have, but so there is no anti-aliasing. So you just refine the settings so that you know from the image that aliasing has taken place or not. Okay. So smaller the phase direction encoding, the larger the field of view. So most often what we do is you take similar resolution, both similar step size, both in delta V and delta U. Okay, just to keep life simple, unless otherwise it's a specific problem. Most often choose delta V equal to delta U. Clear? So now the question is, how do we relate this to resolution of MRI? So what is becoming clear now is MRI scan, they are only covering the frequency space. That too, we are covering the frequency space only finite. Right? If you are recording the signal for TS over a period of TS, right? We already saw the highest frequency is gamma GX TS. Right? So we are covering the signal only over a finite Fourier space. So the actual Fourier transform may be non-zero outside this. The signal might be present outside this, but we have done anti-aliasing, we have restricted to the highest frequency. So Fourier space coverage is your capital U is your coverage in Fourier domain. Like how we use the term field of view, FO of V, X, mean in the spatial domain we said field of view in X direction, field of view in Y direction. We can think about field of view in Fourier domain also. Field of view in U direction can be capital U, field of view in V can be capital V, but we don't call it like that, but that is what. So here what is this U? You know that. Number of samples into the time period between the sample in X direction times gamma Gx. So gamma Gx brings you the frequency because Gx is just the field strength gradient. Gamma is your gyromagnetic ratio which converts, gets to frequency per Tesla. So if you have gamma Gx, this becomes a frequency quantity. This frequency quantity, you have so many samples. You have nx samples, each with a time period t. So nx into t is the total time period of data acquisition, which converted to your frequency. That's what, right? Likewise, you can have your v, which is your in phase direction, ny delta ay times gamma. Okay, that gy is actually there in your ay in the previous slide if you flip back. So what is this saying? This is saying image might have several frequency, but we have acquired the data by applying anti-aliasing filter and having some phase shift in phase encoding. It is implying that you are having data only from a frequency domain space of length capital U in U direction, capital V in any implied low pass filter. The signal exists only within this U and V. That's a rect function. So h of U is rect of U, and therefore your spatial, this is your frequency domain. So in your spatial domain that will be h of x comma y will be sinc function. Rect in frequency domain will be sinc in spatial domain. So now it becomes clear how have we been thinking about resolution even in the other modalities. They're thinking about it as a blurring function perhaps, right? And we said if we know the system characteristic, the spatial PSF, point spread function, then we can characterize or define resolution using the PSF, right, as a full width half maximum. So essentially we are now decoupling the reconstructed signal that we have is actually the ideal signal corrupted or blurred with h of a system function. This dictates your resolution, the point spread function. So we have decoupled recorded signal as an ideal signal with infinite resolution, derated or convolved with your h of xy, which gives you your point spread function, right? So now we need to define resolution as what we have done as width of this blurring function or full width half maximum. This we have done again and again. So now I know my signal, which is a sig function. I can write the full width half maximum. So I will write full width half maximum turns out to be 1 by u. What is this u? This is the extent in u direction. What is this capital V? Extent in frequency domain in v direction. So now you see f full width half maximum is 1 by u. Substitute for u, you get nx delta u. So you already see that if I have more nx, more number of samples and finer step size, right? I mean, if this combination is important. This combination goes up, this value goes down. What do we want? This value to go down means it is better resolution. Full width half maximum should go less and less, right? That is what is better for us, which indicates better resolution. Our point spread is less. Okay. So it is inversely related here. So now increasing u, right? Increasing your u, meaning extent in your u direction, frequency space or coverage area in Fourier space, reduces blurring, which is pretty intuitive, right? High frequencies correspond to sharper transitions in spatial domain, right? That's the intuition that we have. Your sharper or rapid transitions in spatial domain correspond to high frequency. So if I record high frequencies, meaning your U and V are large, then I should be able to catch rapid changes. So that means blurring is less. Okay. But your full width half maximum in X and full width half maximum in Y are determined by the minimal pixel size. Okay. So let's write it out. So what is your pixel size? Let's say if you have acquired the data with m cross n samples in Fourier space. Remember, Fourier space is already discretized space that we have. Suppose we have m cross n samples in Fourier space, we can reconstruct m cross n pixels of the image using inverse Fourier transform. So the pixel size in your spatial domain becomes delta x is field of view in x direction divided by number of pixels that are there. Right? One pixel size in x direction will be field of view divided by number of pixels. Delta y will be pixel size in y direction, which will be field of y divided by n, number of pixels that are there in that direction. Which you can write it as m delta u, n delta v. From the previous slide, you know the field of view x and field of view y are related to inversely to your delta u and delta v. So you can actually see delta x is inversely related to 1 over u, or inversely related to u. Delta y is inversely related to v. Your pixel size in spatial domain is inversely related to the field of view in your Fourier domain. Correct? So it can get confusing. So let's put a slide. Look at this slide. Get comfortable with this slide. Then all of the concepts you'll be able to recall. So this is your acquired data space, where essentially I have samples spaced right with the delta u. This is your u direction. I have samples spaced with delta u. This is my v direction. I have samples spaced with delta v. In the spatial domain, we have delta x in this direction, delta y in this direction. Field of view x direction, field of view y direction. Likewise, field of view in v, field of view or extent in v, extent in u. Look at this relationship. If I have delta u, this is going to dictate my field of view in x. If I have delta v, this is going to dictate my field of view in y. The sampling distance in one domain is going to dictate inversely the field of view in another domain. So likewise, the extent, or you can think about it this way: sampling width in one domain, delta x, dictates the extent in another domain, right? U. Or if you acquire large u, you can have shorter delta x, smaller delta x. If you acquire large v over large v, you can get smaller delta y. Remember, so try to, of course, all of these equations that you see, I'll list it out in the next slide as well. But essentially, you got the concept here. It can be confusing, but if you understand what's happening and you do it multiple times, you will get a feel for it. Then, even if you don't know by heart, you will be able to quickly relate the concepts. So the relationship between resolution and field of view depends on spacing between points in k domain, which is delta u and delta v. Likewise, right? So field of view x is 1 by delta u, y is 1 by delta v, which we saw before. Likewise, your resolution delta x delta y depends on the highest observed spatial frequency, which is u and v. Which is intuitively making sense. Highest frequency is going to dictate your resolution, right? So your delta x is 1 by field of view in u, field of view in y, or capital U and capital V represents the extent of frequency in u direction, extent of frequency in v direction. You can get it like this. Clear? So that's for resolution. Contrast, there is not much that we are going to cover because we have covered this extensively. So contrast is due to two things. One is intrinsic. We covered relaxation times T1, T2 and proton density. There are actually other properties also people are researching and trying to use. Okay, there are chemical shifts. Nowadays susceptibility is becoming a parameter that people are working about. Then flow, tensor flow, you hear about that a lot. So there are other things. We didn't go into the advanced recent ones. We restricted ourselves to intrinsic contrast that are reasonably well understood and currently used in several clinical applications. Extrinsic are your data acquisition parameters, TRTE, flip angle, right? So we already talked about how to maximize internal contrast, right? If you have T1 contrast, two different materials with a different T1 property, you will get the difference as contrast. Likewise for T2. So we covered this signal contrast or weighted, right, for T1, weighted for T2, weighted imaging for proton density. So we will not, there is nothing much to cover on contrast. Rather, we will spend time on noise and therefore signal to noise ratio. Maybe you can always combine that with contrast to noise ratio also, right, later. Okay. So noise. So where is the noise coming here? So the noise that we are interested to cover is coming from during the measurement. Here we do only one measurement. What is that measurement? We are doing a receive coil and receiving the data. That's the only place we are actually doing measurement. Okay. After that, you digitize, you do all computation. So only data noise that comes during data acquisition comes from your receiver coil, and that too is a well characterized statistical fluctuation, because when you have receiver coil and you are doing this operation, it gets heated up. So noise essentially comes from very well modeled Johnson noise or thermal agitation in electronics. Okay, so there is a noise model for this. This is where the noise comes into the measurement, and as you can see, the parameters that are under our control, these are Boltzmann constant, the temperature, right? So you want to do the measurement at lower temperature possible, so that the numerator here gets reduced. Okay, effective resistance needs to be reduced. How do you reduce that? Use small coils. Okay, now you recall we talked about coil design, and I told you that, oh, that's a big electronics measurements part that you can work on. So now you understand where. So if I did wrist, I told you there is a body coil, and then they make dedicated coils, wrist coil, knee coil, head coil, name it, that is there. Why do they do that? Oh, I want to use small coil. So if I want to image wrist, rather than imaging it the whole, the receive coil in the bore, the body coil, I would rather have a receive coil that is small, right? So that I can reduce the noise. Therefore, I can have better signal to noise ratio, right? So reduce noise by reducing this effective resistance, which essentially comes from the body resistance. Okay, then total acquisition time should be as long. Again, this is a trade-off. So already, if you have gone to MRI scanning, you would realize it may be uncomfortable for several. I don't know if you would have felt uncomfortable or not, but most people find it uncomfortable, right? Especially if you are a patient and you are going there, you're breathing, and that causes artifact, and you have to be there. Otherwise, you'll have to make you slow down and then sleep. It can be, so you don't want longer acquisition times. But what our noise says is, so you acquire longer, I will behave well, I will reduce myself. Now that's a trade-off, right? You can already see. R is mainly due to your patient body seen by the RF coil. Okay. So always we are not interested noise alone. Always we are interested noise in terms of signal, rather signal in the presence of noise. So signal to noise ratio, we will recall our signal equation. This is volume, not voltage, right? Volume of the sample. So signal to noise ratio is mean of the signal divided by magnitude of signal divided by square root of variance. So you substitute all this, you get some value. Okay. What we are interested is interpretation. So what is this saying? Increase your signal to noise ratio, increase Vs. What does that mean? I have to have thicker slice. If I have thicker slice, what will happen? Your resolution in the Z direction, larger pixel in the delta Z will become big. So this resolution, so if I am doing axial slices going from head to within the head, right? From or here, I want to have different slices of my heart, axial slices of my heart. I want to have thin slices as possible, so I'll have very many of them. But if I do that, I may lose the signal to noise ratio will be problem. So if I have to increase the slice thickness, I may have only 3 slices covering the entire heart, right? So that means I'll get good signal to noise ratio, but I won't be able to say whether it is in the upper part of the heart or it is, I mean, I won't have any resolution in that sense on slice thickness. One another thing you can maximize is pi by 2, meaning you apply for enough duration so it goes down to the floor. But then increase the scan read of time. Okay, so this is more practical, I mean, and in comfort point of view. That is the only problem with this. This is signal point of view. Okay, so summarize MRI data of a slice. What we saw is nothing but Fourier transform of the effective spin density. That is what is distributed. That is what you are capturing. So you can calculate or reconstruct the image by doing inverse Fourier transform, depending whether on rectilinear scan or polar scan. And we also saw the image quality in terms of resolution. We talked about sampling intervals. Delta U, delta V are the frequency domain. We saw this very confusing, but very, in some sense, if you understand this, very straightforward and intuitive. Nothing, no big deal. If you have higher frequency, highest frequency dictates, in the frequency domain, dictates your finest variations that you can catch, or your spatial resolution. We know that. It comes out very sophisticated here. So delta U, delta V, we related it to your field of view in your XY direction. Likewise, your coverage area of capital U and capital V determine the blurring. And then finally, we talked about Johnson noise and we concluded about signal to noise ratio. Actually, this completes whatever we wanted to talk at an introductory level for MRI. So as you will see, it's a very neat concept and it required so many different fields understanding, right? The scope, if you recall, of our AM 5160 is covering multiple modalities to the extent that recall your objective, course objective. If you look at that image, hopefully you will close your eyes. At least this exercise I would like for you to do. You look at the image, right? You close your image and see, oh, I know how to interpret what this white means, what this black means, what this gray means. I know its units. I know what is the physics of the signal, and I know what instrumentation dictates the limits of or interpretation of the signal that we are having. I think that you should do it for each of the modality quickly. Okay, if it is X-ray CT, I know it's supposed to be related to X-ray attenuation, to the X-ray energy, the materials attenuation property for the X-ray coming at that particular energy. That is a fundamental signal. Then of course you convert the Hounsfield's unit, the X-ray CT image, you will have Hounsfield unit. And then likewise in your ultrasound, we send sound, you receive sound. So essentially we are characterizing the scattered signal, that is the echo that is coming back, at least in the echo mode that we covered. You send the pressure signal, it's scattered. How much is scattered from a particular location depends on the acoustic scattering property, which is related to acoustic impedance properties. So the reflectivity at each location is what we are going after. Here in MRI, you have several different properties that are coming in. Right there, it was mu in CT, X-ray based CT. Then we talked about only essentially your acoustic scattering or impedance mismatch that gave out. Whereas here, look at the different fundamental properties of the tissue that is happening. Spin density, the relaxation time in transverse, relaxation time in longitudinal. This is what we covered. There are other parameters as well. Okay, so I think this summarizes what I wanted to cover. Please play the video several times, get yourself comfortable.